Hello and welcome to our presentation for our project, Standard Operating Procedure for Whiplash Testing to Improve Automotive Safety for Females.
This is the project team. We'll be discussing our chosen problem, approach to design, final design solution, and design defense.
Females are at a significantly higher risk of sustaining injuries in automobile collisions when compared to males. This increased risk is directly attributed to the current state of automotive testing. Currently, a 5th percentile female dummy, which is a scaled-down version of a male crash test dummy, is used to represent the entire female population, as seen in the picture on the slide. Additionally, there is a lack of equivalent testing between male and female crash test dummies, where in some cases the female is completely overlooked. Due to this inaccurate representation of females in current testing procedures, safety features of the vehicle are not designed with females in mind. For example, whiplash protection systems like reactive head restraints were found to be 65% more effective for males than for females.
The scope of the project will be limited to whiplash-related injuries, as they present the largest discrepancy between males and females. Most of these injuries occur in rear-end collisions, and therefore the scope of this project has been narrowed to test only rear impacts. The solution outlines a test procedure for the average female that will be used as an addition to the current testing. This project is designed to meet all legal requirements in Canada as well as the US to ensure it can be implemented throughout all of North America. It is likely that current vehicle designs will result in failed tests when this procedure is completed, requiring the redesign of vehicle safety features. Since the specific changes automotive manufacturers make to vehicle design cannot be predicted, neither can the environmental or economic impacts of these changes. Therefore, this is outside of the project scope. The purpose of this project is to design a standard operating procedure for safety testing of the 50th percentile female, which can be easily implemented in the automotive industry to reduce the risk of whiplash-related injuries in rear impact collisions.
The design process began with in-depth research into current safety testing and regulations. Current testing procedures and protocols were reviewed and evaluated. These procedures provided a list of features and functions that the SOP must include, such as injury criteria and performance levels to be met. Based on the ways in which automotive testing can be conducted and the technology available to represent and test the safety of the average female, we created conceptual design alternatives and compiled them into decision matrices to be assessed and evaluated against one another.
There were determined to be 3 main components of the design: the crash test dummy used, the dynamic test method, and the method of implementation. There are 3 dummy models available for use that accurately represent the 50th percentile female. A prototype dummy, BioRID 50F, was developed by the AdSeat project, which is a project that evaluates the protective performance of vehicle seats to reduce whiplash-related injuries. This prototype was developed by physically modifying the BioRID male dummy components such that they were scaled down to meet only target dimensions and masses for the average female. The second alternative is the virtual EVA-RID finite element model. The EVA-RID model was also developed by the AdSeat project and has been validated as an accurate representation for females in rear impact testing. The third option was a finite element head and neck model. This model only represents the head and neck segment and does not include reflexive muscle responses, limiting the criteria that can be assessed.
There are 2 dynamic test methods currently used in virtual automotive test protocols: car-to-car testing and sled testing. The benefit of virtual testing is its accessibility and ease of use. The time and resources required to execute a virtual test are also significantly less than those required for physical testing. There are 2 possible methods of implementation of the SOP. If the solution is implemented as a voluntary certification, it would greatly appeal to the automotive industry as a marketing tactic to claim that their vehicle has been tested and approved for the safety of an average female. Alternatively, implementation of the SOP as a legislative mandate would maximize the social impact and number of females positively affected, as the industry would be legally required to implement the updated safety procedure.
The first 2 constraints are that cost and time must not exceed 200%. The SOP must specifically test the safety of a 50th percentile female without compromising safety for another demographic. All components of the SOP must currently exist, and the procedure must be repeatable and meet all applicable legal requirements. The criteria include that cost, time investment, and environmental waste are all minimized while the social impact of the procedure is maximized. The autonomy of the SOP should also be maximized, as well as the number of international legal requirements that the SOP meets. Finally, the dummy should be as representative of an average female as possible and easily obtained.
The final design solution was produced based on this approach to design. The SOP will require use of a crash test dummy that was designed to represent the average female. This was chosen to be the EVA-RID finite element model. The SOP includes a static measurement, which measures the seat and head restraint geometry, and a dynamic test, which assesses the seat and head restraint's ability to prevent injury in a collision. The dynamic test was chosen to be a sled test, as this is consistent with current whiplash tests required in Canada, the United States, Europe, and Japan, among other places. The seat adjustment and dummy positioning procedures have been designed to accurately represent how females adjust and sit in their car seats. The injury assessment criteria limits have been designed to be unique to females and are based on how females respond during a crash and their risk of injury. Lastly, the SOP will ultimately be implemented as a legislative mandatory.
The SOP will be a computer simulation test that uses the EVA RID finite element model as the crash test dummy. EVA RID is a commercially available virtual dummy that was created by Swedish researchers as a part of the ADSEAT project. EVA RID was designed to meet the mass and geometry of the average female, which is approximately 5'4" and 137 pounds, and the stiffness and damping properties of the neck and spine were reduced to 70% of the male dummy in order to represent other biological differences between males and females, such as lower neck strength and higher flexibility. The response of the dummy in a dynamic crash test was analyzed and compared to female volunteers and accurately represents how female bodies react in a crash. The image here shows a comparison between EVA RID and Bio RID, which is the male finite element rear impact dummy.
The static measurement test measures the size and geometry of the seat and head restraint, and the limits presented here are specifically designed for an average female. The diameter of an average female's head is 156 millimeters, which is smaller than an average male's, so the current minimum width of the head restraint, which is 170 millimeters, has been adopted. For proper support, the top of the head restraint should be in line with the top of the head. Based on the torso, neck, and head lengths, as well as the torso angle for the average female, the minimum height between the H point of the dummy and the head restraint at its highest position must be at least 666 millimeters. The distance from the back of the head to the front of the surface of the head restraint is called backset, and it should be minimized whenever possible. Females sit on average with a backset of 40 millimeters, which is 41 millimeters closer to the head restraint than males. Therefore, the current backset limit for males of 55 millimeters is acceptable and conservative for females.
The positioning procedure is how the EVA dummy must be positioned in the car seat that is being tested and how the seat must be adjusted. On average, females sit with their seats inclined 3 degrees closer to vertical than males. The angle that the seat is reclined from vertical is called the seat back angle. Since males typically sit with a seat back angle of 25 degrees from vertical, the angle for this test should be 22 degrees from vertical for females. As mentioned before, on average, females sit with a backset of 40 millimeters, so the dummy should be positioned as such whenever possible. And finally, the top of the head restraint should be positioned in line with the top of the head. The figure on this slide summarizes the static measurement and positioning procedure values for females.
The dynamic test involves applying 2 acceleration pulses to the sled to simulate a low severity and high severity rear impact collision. In both of the simulations, several whiplash injury criteria must be met to pass the test. The following criteria have been changed and designed to assess the risk of injury for the average female. This was accomplished through literature review, biomechanical calculations, and applying scaling factors to consider the differences in mass and dynamic responses between male and female. The head injury criteria, which is the maximum acceleration at the head center of gravity between 2 points in time, should be less than 700. The NIJ, which measures the loads and moments on the upper neck, should be less than 1 at any point in time. The peak tension and compression forces on the upper neck should be 3,584 newtons and 3,438 newtons, respectively. The load on the neck before contact with the head restraint, or the NIC, should be limited to 12 meters squared per second squared. Finally, the NKM, or load on the neck when in contact with the head restraint, is calculated using 3 different values. The critical intercept values that should be used are 29 newton meters for extension moment, 53 newton meters for flexion moment, and 507 newtons for shear force. This criteria must be met during testing to prove it adequately protects females during collisions.
Lastly, we chose that the SOP will be implemented as a legislative mandatory. A legislative approach will allow the SOP to have greater outreach than only involuntary certification. It is more likely to cause widespread change and improve the lives of many females, and encourage further automotive and safety testing design improvements. Although a legislative mandatory is the end goal, it requires time for the test to be accepted and additional lead time to be implemented. So, as the procedure goes through this process and before it becomes legislation, it will be a voluntary certification for manufacturers. This will be a significant selling point and will bring in additional revenue from female consumers who care about their safety.
Now we're going to move into design offense, justifying why the solution solves the problem. The purpose of this SOP is to increase automotive safety. While in use, the SOP does not put any person using the SOP at risk of harm since it is entirely simulated. However, as the purpose of the SOP is to improve the safety of females while driving, it is working effectively if it increases the automotive safety of females as a result of the testing being conducted. This is because there is a clear connection between lack of testing and risk of injury in car accidents. Since there is less safety testing conducted for females in vehicles, they are more at risk of being injured or killed in car accidents. If additional safety testing is conducted for females, the risk of injury or death in car accidents should decrease. The intricacies of this connection will be discussed later.
The desired outcome of this SOP is to disrupt the current practices of automotive safety testing and vehicle design to change how it is conducted in relation to women. By accurately representing the female body in safety testing and regulations, we believe that this SOP will lead to improved vehicle design and result in a decline of injury and death for women and all people who may drive a car. This improvement will gain momentum from social and economic pressures and reap social and economic benefits, but there are environmental concerns to consider that will be discussed in the next slide.
This table shows the types of pressures fueling the SOP, a flow of outcomes as a result, and the overall outcome of the SOP. There are two social pressures which help the SOP to function as intended and create change in the automotive industry. First, women make up approximately half of all drivers and should be treated as such, and second, social justice issues such as gender inequality in automotive safety testing spread quickly and gain momentum through social media and the internet, and people influence each other and demand change through these tools. The result of the SOP will be that the public becomes aware of how current safety testing is conducted and lacking in representation. Hopefully, this will cause other testing procedures to be updated as well to include the average female and possibly more demographics. This will lead to dummies, either physical or simulated, being created to represent different body types and demographics. As a result of all the new testing, some vehicles may fail, and this, along with social pressures, will force car manufacturers to reevaluate their vehicle safety designs, improving them and reducing injuries from car accidents. There are also two main economic pressures fueling the SOP. First, women influence 84% of all purchasing decisions, and second, women are more concerned with safety when buying a car and spend more time researching before making a decision. As a result of the SOP, it is likely that women will only buy cars that test safe for women. However, combined with the social impacts and awareness, women may use their purchasing power to influence car manufacturers to improve vehicle safety designs in order to remain financially successful. This creates a new facet of market competition between car manufacturers, and since competition breeds innovation, they will again be pressured to improve vehicle safety design in order to maintain or gain market share, thereby reducing the risk of injuries from car accidents. Finally, the SOP requires a powerful computer to run the simulation software. Although simulations decrease physical testing and the waste associated with that, there is an increase in energy demand which could be coming from polluting sources such as fossil fuels. Additionally, increased use of computers increases the toxicity and environmental degradation associated with the life cycle of a computer, from mining materials for the batteries to disposing of the electrical components after its useful life. Another environmental concern is that the SOP encourages new vehicle design, and this has the potential to be a wasteful process. Overall, once the safety in vehicles is improved, it is possible that many people will dispose of their unsafe vehicles, creating more waste.
There are risks and uncertainties mainly associated with the required performance levels in the design solution, but also regarding how the SOP will be received by the public. Although the performance levels were based on logical assumptions, there was a limited amount of data for these calculations. The next step in the design process would be to conduct experiments to support these limits. There is also some uncertainty regarding social reception. Since this is an issue we care deeply about, we assume that other people will also care about this social injustice and see the design in a positive light. However, there are other social issues more prevalent than this that are also not being resolved, so the issue of inequity in safety testing could be treated the same and not spark the change that we hope for. There is some economic uncertainty in assuming that females have enough purchasing power to influence car manufacturers to improve their vehicle safety designs. Lastly, although this is an issue that would ultimately be economic to solve sooner rather than later, the fear of large initial costs, such as those related to vehicle redesign, may be a barrier to car manufacturers from investing in improved safety designs.
We present 3 recommendations to continue the change this project should inspire. First, conduct experiments to ensure that the performance limits accurately represent women. Second, encourage simulated automotive safety testing for more demographics. And third, promote diversity in the automotive industry. We believe these steps will continue to improve automotive safety for all.
To conclude this presentation, here's a quote from Emily Thomas. "The reality of progress in automotive safety is that it heavily relies on regulation." Thank you for listening.